Now that we've covered all the various types of transformations, this last section, or the next to last section, is really going to combine them all. So again, we looked at horizontal and vertical translations, and horizontal and vertical stretches and compressions and reflections. So today, or this video, we're going to be able to graph functions of the form. So talk about this generic form, when we have a function f of x, we have something multiplied to the outside, so that's our a attribute. And again, that's going to cause either vertical compression or stretch or reflection, times f of f of k. So again, we're multiplying to something to x inside our function. So this is either going to cause a horizontal compression or stretch, or horizontal reflection. And also inside our function, we could also add or subtracting something to x. In this case, the attribute d. Again, this is going to cause our graph to shift either left or right. And finally, going to add or something outside our function. And again, this is going to have a translation or cause a graph to shift up and down. So we're going to use what we call mapping notation to appropriate transformations to points on the parent function. Lastly, we're going to state the transformations of functions of the form a of f times k times x minus d plus c. So we're going to be really comfortable with this form, this function notation of a transformation. Because once we get the four attributes in there, the a, k, d, and c values, one, we could describe the transformations, and second, be able to graph it using mapping notation. So in the previous sections from 3.3 and 3.4, when we looked at the vertical and horizontal translations and reflections and compressions, hopefully you can understand why and how that happens. But really in the gist of it, in 3.5, when we combine everything, if you can understand and use mapping notation, that's really all you need in order to graph any transformation of a function. So when graphing or determining transformation of the function, it is really important to identify the parent function if graphing so that we know the general shape of it. So if it's a root function, we know it's a shooting arrow. If it's the absolute function, we know it's the V-shaped graph. If it's the reciprocal, we know sort of that graph that's split into two, that happens in the two different quadrants. And then finally the cubic, well, we know it's a yin-yang shape, and we can even extend it to something like a quadratic, where we know something is x squared, we know it's going to shape a parabola. Algebraic, we're going to be able to algebraically convert the function to the form, so to the general form, a of f times kx minus d plus c, that is, identify the a, k, d, and c attributes. So it's really important as we look at this that we must factor inside the brackets, inside a function, in order to read off the horizontal shift correctly. This is because when we look at the horizontal translations, we actually want k multiplied to the value of just x. Not just, so we need to factor that out because really we need to apply the stretch first before we apply the shift. So as an example, we might have a transformation g of x is equal to minus 2 f of, in brackets, 4x minus 12 plus 1. So here we have a transformation of a function f of x. What that actual function is irrelevant. So it could be root x, it could be absolute value of x, it could be reciprocal of x. It could be f of x, could be anything. But here, the important thing is that we could identify the transformations and then therefore describe how it would be transformed, even though we don't know what the parent function is. But if we're given the parent function, then all these transformations will apply to that parent function, whatever it is defined to be. So the correct order to state the map all transformations is we must identify stretches, compressions, and reflections first, because that's really what's going to happen to the graph first, and then talk about the shifts and the translations. So as I mentioned, we need to factor out the k value first. So let's go g of x is equal to negative 2 f of, and so this is where the square brackets come in, because when we factor out negative 4, we are going to get x plus 3, plus 1 on the outside. So here, when we factor out the negative 4, we're actually going to get the proper shift value. In this case, we can kind of see it's going to be 3 to the left. If we didn't do that, then we might falsely assume or falsely see that the shift is going to be 12 to the right. Since we're kind of seeing this, it might interpret that. But really, we want to get x by itself, so that's what we need to factor the negative 4. In other words, not anything multiplied to x inside of brackets. And therefore, we could read the proper shift value. So now that we have that, there's my a value, there's my c value, there's my k value, and there's my, well, how I would get to d value is I need to look at all that equals what makes that 0. So here I'd like to identify that. So my a again is negative 4. My k, since we need to look at the stretches and compressions first, let's look at k. So I guess the k is also negative 4. Oops, I sort of misread that. A is not negative 4, a is negative 2. Jumping the gun there. My d value, so I'll stay inside my function here. Again, what makes that 0? That's going to be negative 3. And then my c value is my outside, what's being added or subtracted on the outside, and that's going to be a 1. So there I could describe my transformations. So here this is going to be vertically stretched by a factor of 2. So again, we need to look at the absolute value of a. In this case, it's going to be 2. Since it is greater than 1, we know it's stretched. But since here it's also negative, we must say that it's vertically reflected. Then we look at our k value. Since k, the absolute value here of k is 4, in this case is greater than 1, this is actually horizontally compressed. By a factor of, so again, for horizontal stretch and compression is 1 over k, or the reciprocal of k, but the absolute value of that, so this is going to be by a quarter. And this is also horizontally reflected, or reflected in the y-axis. I would accept either. And then now we could identify the shifts. So this is shifted 3 units to the left, since d is negative, and 1 unit up, since c is positive. Okay, so that's how we go off and describe the transformations based on our a, k, d, and c attributes. So what is what's the mapping to the graph of the above function from its original parent function? So here is a general mapping notation. If we have a point x and y on our function f of x, and that function is being transformed to, again, a, so f to a function g of x, to a f of k x minus d plus c, the new point, or the points on our transform function, is going to be, for the x value, is going to be x over k, so sort of dividing by k, multiplying by that compression or stretch factor, and then we're going to add d, so that's our new x value, and our new y value is going to be our a value times y plus c. Okay, so really we need to know that. It's going to come back time and time again, and this is really a shortcut to graph any transformation that you're given. So for example, we're given this function g of x is equal to 4 times everything inside the square root here of negative 2x minus 8 plus 3 on the outside. So we want to state the parent function and the transformations to the parent functions. Also at the end, we want to state the domain and range of g of x. So this is a little bit trickier to do, but once we graph it, we can see it, and also explain how we've been able to get the domain and range, even by looking at the transformations that was happening. So let's define our parent function. So f of x is going to be my square root function. So f of x is root x. And how could I write this in function notation? Well, I'm going to do negative 4 f of, so whatever is inside my square root is going to be inside my brackets, minus 2x minus 8 plus 3. So we're going to take one extra step because, as we mentioned above, really we need to factor out the coefficient to x to get the proper shift value. So here is going to be really negative 4 times f of minus 2x plus 4 plus 3. So let's quickly identify my a attribute. My a attribute is negative 4. My k is a negative 4 as well. So not really the best example because both values are the same, but we'll see what we're going to be doing here. The d value, so what makes that 0 in the inside the brackets? Oh, I did it again. The k value, it's not negative 4, I'm jumping the gun. The k value here is negative 2. As my d value is negative 4. And then my c value here is going to be a positive 3. So how do I define my mapping notation? So again, x of y goes to, in this case, x over k plus d, a times y plus c. So we're going to write that out. So we're just going to be sticking it in our head so that we're going to have memorize that mapping notation. So let's plug in the value. So x comma y goes to x over negative 2. So d is going to be plus a negative 4, so this is going to be minus 4. And then my y value is going to be negative 4y plus 3. So what are the key points on my parent function? So f of x here is root x. What are my key points here? That's going to be 0 and 0, 1 and 1, 4 and 2, and 9 and 3. So in order to get the new points on g of x, we're going to apply the mapping notation to my points on my parent function. So let's go through the x's first maybe. So let's do this systematically. So here x is going to be 0 over negative 2 minus 4. So 0 divided by anything is going to be 0. So my new transform point for x is going to be negative 4. Then we take the 1. So here's going to be 1 over negative 2 minus 4. So that's going to be a negative half minus 4, which is a negative 4.5. Then we take the next x coordinate, so 4. So here we're going to be 4. So plugging that into my mapping notation here. So 4 over negative 2 minus 4. Well, 4 over negative 2 is minus 2. Minus 4 is going to be negative 6. Now finally we have 9. So 9 over negative 2 minus 4. Well, 9 over negative 2 is going to be negative 4.5 minus 4. That's going to be negative 8.5. So there's my new x coordinates. And we're doing the same thing now with the y coordinates, but we're applying it to that part of our mapping notation, and we're getting a new y coordinate. So here we're going to be the y is 0, so we need to transform the y coordinate of 0. That's going to be negative 4 times 0 plus 3. Well, negative 4 times 0 is just 0, plus 3 is 3. Then for y equals 1, that's going to be negative 4 times 1 plus 3. Well, that's the negative 4 plus 3, which is going to be negative 1. And then y is 2, so it's going to be negative 4 times 2 plus 3. Well, that's going to be negative 8 plus 3 is going to be negative 5. And the last one is when y is 3, so negative 4 times 3 plus 3. So that's going to be negative 12 plus 3, which is going to be negative 9. So here's a new point, negative 4 comma 3, negative 4.5 comma negative 1, negative 6 comma negative 5, and negative 8.5 comma negative 9. I was going to say we should look at the transformation so that when we look at the graph, we can see that we actually did our arithmetic correctly or did the mapping notation correctly, but it does say to state the transformation. So let's actually do that. So since a is negative 4, so this is vertically stretched by a factor of 4. It's also vertically reflected since A is negative. This is also horizontally. So absolute value of K here is 2. So that means it's going to be, since it's, I think of it as the opposite of vertical. So in this case, it's greater than 1. So this is going to be horizontally compressed by a factor of, in this case, 1 over K, which is going to be 1 over 2, the absolute value 1 over K. This is also horizontally reflected. And then our two shifts shifted up 3 units and 4 units to the left. So hopefully when we graph this, that's what our transformation is. That's what we're going to see. So we see a double reflection, vertical and horizontal. It's going to be vertically stretched and horizontally compressed. So we're going to see that, we'll see the net effect of that. So here we got X and Y. I don't want to go into that too much detail. Hopefully we see it afterwards. But as I kind of mentioned before, when something's actually horizontally compressed, it actually is going to vertically stretch it a bit. So because it's already vertically stretched as well, this is going to be looking like a big vertical stretch. So there's my X and Y, and let's label our axes or scale 2, 4, 6, 2, 4, 6. And let's plot a new points, and maybe I'll do this in red. So we have -4 and 3. So -4 and 3 takes us down over here. Oops, no, it's +3. -4 and +3. Then we have -4.5 and the -1. So -4.5 and the -1 might be right there. -6 and -5. So 2, 4, -6. Oh, I missed a 4.5. It looks like 5.5. So -4.5 and -1. -6 and -5. So 2, 4, 6 and -5 will be down here. And then finally the last point is -8.5 and -9. So -8.5 will be somewhere over here. And -9 is over here. Okay, so we know that this is the general shape of a shooting arrow because our parent function is root x. So that's how we connect the dots. And it's going to go out like that. So there's our function, g of x. So this is definitely horizontally reflected. It is also vertically reflected because I was going down and going to the left. And this is definitely vertically stretched and horizontally compressed. Begin looking at horizontal compression, it actually has the appearance as vertically stretched even more. So the last thing we look at is the domain and range. So the domain of this function is XER. In this case, x is less than or equal to -4. And the range is YER, and y is less than or equal to 3 in this case. So we can easily see that from the graph because we see that everything is to the left of -4 and below 3. How we could actually see this while actually graphing as well, if we understand our parent function, root x. Well, we know that the domain and range of root x is greater than or equal to 0, and y is also greater than or equal to 0. Since this is vertically reflected, so it's going downwards, that means that y will have to be less than or equal to 0. So that affects our range. So really, whenever reflection, we change the greater than to less than or equal to 0. But at the same time, this is also shifted up 3 units. So instead of being less than or equal to 0, it's actually going to be less than or equal to 3 because it's moved up. So that kind of makes sense, and that falls into what we have for the range. Likewise, with the domain, normally the domain of root x is greater than or equal to 0, but we horizontally reflect this. That means we change the relative operator, and it's going in the other direction. So really, x is less than or equal to 0 when we're horizontally reflected. But we also move this 4 to the left because the d value is -4. So really, x is going to be less than or equal to -4 since we shifted it to the left as well. So that's how we could sort of algebraically determine from our transformations what the new domain and range is by having an understanding of what the domain and range is on our parent function. So how can we summarize this? So what we want to do is we want to make sure when we have a transformation, we want to convert it to this form, a times f of k times brackets x minus d plus c. In other words, we want to factor out the k value, whatever is multiplied to x, so that we get the proper shift value. So where f of x is the parent function, and now we can clearly identify the a, k, d, and c attributes or values. Okay, so here's a summary of all the transformations that happen. Okay, so our a, so this is no different than for a parabola. So this is kind of a review as well, but now we know that applies to all functions in general. That if a is negative, it is the graph is reflected in the x-axis. Okay, so really what I'm saying is a determines the vertical stretch or compression, or whether or not it's reflected in the x-axis. So if it's negative, it's reflected. If the absolute value of a, in other words, ignore the sign on a, is greater than 1, then it's going to be vertically stretched by a factor of the absolute value of a. On the contrary, if absolute value a is less than 1, then the graph is vertically compressed by a factor of absolute value of a. Looking at k is going to determine the horizontal stretch or compression, and whether it's not reflected in the y-axis or we have a horizontal reflection. So to me, how I try to remember this is really in terms of stretch and compression, is the opposite of a. Well, this thing that's similar is that if k is negative, we actually have a reflection. This time, though, is horizontally reflected. If the absolute value of k is greater than 1, what's going to happen is the graph is actually horizontally compressed, and the factor is 1 over k. If the absolute value k is less than 1, then again, like I said, sort of the opposite of a, the graph is actually horizontally horizontally stretched by a factor of 1 over k. What you will hopefully recognize is that regardless of whether it's a horizontal or vertical stretch or compression, if it's a compression, the factor will always be less than 1. And if it's a stretch, the factor will always be greater than 1. So this applies whether it's horizontal or vertical. So that's sort of a double check for you. If you say that something's horizontally compressed, that factor must be less than 1. And if you say that something is stretched, that factor must be greater than 1. Okay. Then finally, to summarize the last two transformations, which are the shifts, the easier one. The value of d, so whatever is being added or subtracted to x inside my function, is a horizontal shift, what we call translation. If d is positive, that means the graph is shifted d units, the absolute value of d units to the right. And if d is negative, well, the graph is really shifted the absolute value of d units to the left. When we look at the c value, in other words, what's being added or subtracted outside the function, this determines our vertical shift or translation. If c is positive, that means the graph is shifted up c units. So the absolute is redundant there because if c is positive, it's actually going to be a plus sign. But if c is negative, the graph is shifted absolute value of c units down. Okay. Again, the main thing of this lesson as well, when we're looking at graphing this, is to use the mapping notation. So if we're given the form g of x is equal to a times f of, in brackets k, brackets x minus d, plus c on the outside, then we could use the mapping notation of x over k plus d, gives us that new x value, and a times y plus c gives us that new value when we were given a point x comma y on our parent function. So right now for homework, we'll give you a handout to do, plus on page 129, several practice questions. So really this is the culmination of what we want to really grasp in this unit, other than inverses, which is something totally different. But in terms of transformations, this is the entire summary, and this is the entire combination or culmination of it.